All right, it's a pleasure to introduce Lee, who will be speaking on factorization and chiral algebras.
Yep. Thank you for the introduction. Okay, so as I must say, I haven't understand how all these tools fits in the big geometric numbers picture. So this will be a shallow talk, only concentrating on these themselves. Okay, so okay, so let me fix my setting. Emax would always be smooth proper curve. Throughout the talk. And okay, so first section would be just introducing factorization. So I personally find factorization, the factorization algebra is equivalent to chiral algebra, but I personally find factorization, this definition of factorization algebra to be more natural. So let's actually do the definition of factorization algebra first. So module. Okay. Is there a cutoff line down a bit?
Everything's visible.
Everything is okay, good. Okay, so what do we want? So we want okay, so we want a certain collection of modules over any copies of X, which have this factorization property that we've seen for spaces Venice and Dreamfield, F many. So we want at the very least we want quasi coherent sheaf over the space lags of X, where I don't specify the number of X. And also see those compatibilities along the diagonals and then along the off diagonals. Okay. So a very natural thing to work with is the following space called the Rand space. So at least if X is a topological space, you know what it is. So it should be just classifying non-definite subsets of X. And well, such a quasi-coherent sheaf should be quasi-coherent sheaf over Rand X, but doesn't make sense because I haven't give Rand X algebraic space structure, and actually I don't think it has that good algebraic space structure. But let's say for topological space, it has a good topological structure. Namely, I can write it as the column along the diagonals of the finite copy of Xi. Okay, and those diagonals will be closed invariants, and you can put the topology on Rand X just to be the topology that makes the column, each of the invariant of the column map to be continuous. Yeah, so namely, well, an open set in here is open if and only if each go back to each of the Xi here. And the property says that well, X is connected, and Rand space is weakly contractible. It says, well, what is weakly contractible means? It just means all the fundamental groups are true. It's pretty easy to imagine. You have finite collection of points. It is a question of more. Okay, so well, as long as it's connected. Okay, but how to formulate the algebraic analog of all the story. So it turns out it would be this so-called factorization algebra. Well, factorization algebra is so then it's satisfy more properties than just quasi-coherent sheaf over Rand space. I would still say it's an analog. factorization algebra and well, you need some like commutativity invariance here. It's like give you like this sort of like contractibility property. And what we'll see is that the analogy like in the algebraic world is like the factorization part. Yeah, I hope this is kind of a motivation or like at least an introduction like to the world of such ideas. So let me now start with this algebraic word. So we need, well, first to see like what is quasi-coherent ratio for this rank space. Okay, but I have already like written down this column definition, so I can just take the quasi-coherent ratio that would be the name of the quasi-coherent ratio on that side. But I just write everything down more. I'm pretty sure you know what to do now. So X, just a collection for each I in this exercise of quasi-coherent which has satisfied the compatibility along these transition maps in made diagrams. Right? So a fraction of xi for any I, and also this isomorphism is part of the data. The isomorphisms for any k goes to I projection. I want it to be like part of the data. So d pi is like the go back along the diagonal induced by like, so you have like xi injects into x3 close embedding, pull fj back. Correction of quasi-coherent sheet is called fi. Finite. And compatible with comes. I won't say anything about compatibility later, but now let's just okay, so two things. One is that maybe you want, maybe you ask yourself, well, why do I do a quasi-coherent like instead of a D module? And then like the answer is that, well, when we see like, when we put on like this more condition about like factorization algebra, like once you have this like factorization property, like you would automatically have like a D module structure on each of these. Okay. And the other thing is that, well, I think this is a minor condition, but like, okay, so the next notes that like follows says that, well, moreover, we require there aren't any like junk sections, so you don't want like any sections to be like supported on the diagram or any of the diagram. We require F2, let's say. F2 just means F for like a two elements set I. You have no sections supported on the diagram. Okay, so now we moved on to like find like put on like these factorization conditions. Okay. Part of the definition, so like non-unital. We'll also do like unital next, but like when I talk about factorization algebra, it always means unital. When I talk about non-unital factorization algebra, I always put the word non-unital. B quasi-coherent red space defined in part 1, but also we wanted to have like, namely like if I have like a decomposition of well just x2 like off the diagonal, I want it to be like the box tensor, right? So with isomorphisms, C alpha is like the general form. Box tensor should be like the same as like the union along the off diagonal or of finite sets, and they alpha is like this u goes to xi, and u is like those for like the coordinates in like different I and ij's. You want those coordinates to be like this. Okay, so u is like okay. So this is quite usual. And so what do I mean by unital? One say unital as a factorization algebra. Non-unital plus a unit. What is a unit? So one particular example of a non-unital factorization algebra is just you take BI to be like the structure sheet that for any I, right? So you just ask to be like there is a map from like this O to B satisfying some unit axioms. Map of factorization algebra. O goes to B. O is the factorization algebra, I just say that word. Of non-unital factorization algebra, such that where I need B inside like B1. B1 is unit axiom, so I can consider like one box B, right? Inside, well, this B is a local section. Uniquely adds to from saying 2. That's just because J pullback of B2 is the same as the pullback of B1 box B1. And also, like I think this condition, no section support on the diagonal tells you that there exists a unique difference. Okay. But the theory one is that this guy is already defined over the open and uniquely extends to like the whole thing over B2, and we want like it's like go back to like the diagonal to this itself, right? So have such that delta means the pullback to the diagonal. It's just B. But we also know that B2 pullback to the diagonal is B1. Okay, so so that finishes like the definition of the factorization algebras. Okay, a little quick. Let me just say a remark. You might wonder, like, well, here's just about B1, B2, but like I want such a map. Where it is. So O goes to be such a map of factorization algebra give you a certain like unity like all BIs. So also want like those unity BIs, so you want like a more generalized version like B, maybe BI and BJs, and the unit acts on its fact by unit, and it's actually true. It also follows from this sort of thing. And remark that a quick exercise for tells you we have maps constructed similarly. You want just do like two single x, but like do xi1, xi2, xi2, and well by the unit map given by like x2. Then for any f from like I to I1, do like I from the unit of I1. So by setting the map on I1 to be like identity and on the I2 to the F. Satisfy property that's diagonal corresponding to this pi. Pull back diagonal to B, box 1. Inside what? Inside, yeah. Okay, so this is also, that's actually also true and just follows. Second is yeah, the one that we set, and if factorization algebra actually is unique. Any factorization algebra is with the canonical natural D-module structure. But well, this is basically you just like compare like this map and like if you swap like the row, or if you set I1 equals I2 and swap the row and you get isomorphism between like B box and O box. That's how you get it. I'll talk about that more in detail like when I talk about the equivalence with scalar algebra. Okay, but it might like a natural well on all right.
That's working for any element for XXV.
I'm
Like the
I don't know if the claim is true of general X, but I think it's still true. Yeah. But like the usual scenario will be. Yeah, it just follows. I'll say one word about equivalence with Chiral. Okay, so the third. Well, okay, so like so this this category of factorization algebra is a monoidal. There's obvious notional tensor product, like D1, D2, algebra. And so there. Tensor product is to be obvious thing. Yeah, that's a product of corresponding particular module on that side. And this is obviously okay. So definition of factorization algebra. So the next thing I would do, right? So factorization algebra and factorization homology, and define a factorization homology. So for factorization algebra, D over X sets of define factorization homology as this part is just notation. We want it to be just okay, so it has a B module structure, so sorry, D module structure, so it's like naturally if you think about it as a classification like over the rank space, it also has the D module structure over the rank space, whatever that means. So this one you want to set it as the round chain complex over line X over E over line X, but like concretely, what does it mean? This means it's the coding of on these eyes. Well, right, so we write down that coding expression there. So the transition maps are all like closely thematic and take like the ground chain of like this factorization module over the structure. So this well, X is proper. Sorry? X is proper. Oh, so I don't need X. But I think there's a general comment saying something like in general, like it's not proper, then you need to do like compactly supported cohomology, but like the compact supported cohomology for D module is not so good. Like you should like except for like those D modules. Like, so well, okay, but for us, okay. All right, so this is quite abstract definitions. But the proposition that's like analogous to like this, what is it? To the fact that ran X is like quickly contractible is just the same as naturally guess, but I won't prove. Cover me a proof. That parallel homology for this trivial factorization algebra. Okay, so this finished like this analogy, and let me give some example of like factorization algebra. So I have a second, and I don't have a second. So recall that we have this space in Dreamfield Grassmannian, where I is like classify like G bundles where I can do like I modifications along like the sets XXV to the trivial one. And he is the realization of the G bundle along the complement of the XXV. Okay, so it naturally have the projections to the highlights, and where I satisfy factorization property for the space. I won't say what it is, but it's usually here. Okay, if you're like this joint is just product. So one can take certain quasi-coherent shift coming from like this projection, right? So the easiest one would just be to be like just the push forward of the structure shift, or more generally, push forward of let's say any canonically defined shift. I think, well, for example, like we consider some sort of like Raphji check like over the rank space, then you should thing like Raphji check rank space would associate like a shift over like or the fraction of a shift over like I or something. But I won't talk about that. Just example would just be like push forward of structure shift. Okay, so
sorry, can you what type of push forward are you talking about?
Okay, if I take like the quasi-coherent shift version of the, I think.
So the quasi-go push forward will be very bad, right? Because this thing is an end scheme. Yeah. So you could do either end-co push forward, or you could do like a theorem push forward if you're working with D modules everywhere.
Yeah, I think if I work with D module everywhere, I just take like a theorem push forward.
Yeah. I mean, you take it like push forward. Like you can do both. The interesting example is when you take push forward, it's like a phone or one of them will be like coherent homology in BunG, and the other one will be much easier formula for the offline.
redundant? Is it redundant?
No. The one when you use just the cohomology is feature. Yeah. Anyway, I mean, yeah, both push forward will be something, but then no.
If you do the INSCO push forward, then factorization modules for that thing is the one that it's sort of, sorry, it's the one whose factorization modules control like integrable Katsumudi representations. That's definitely something you can do.
Okay, so these will be like the examples, and well, so I want to. Okay, so I want to also define like the modules, right? So definition. Factorization. Okay, so factorization module over factorization algebra. Well, it's just like you use this diagram that well that added like a star to like denote like the place where the module is, right? So factorization B module M is a fraction of B modules. I tilde x I tilde. Well, I tilde is just I plus like a quant. Then for any now you want to like allow like some like condition of like the points in I with the star to mean like the ring multiplication onto the board. Okay, so surjection such that right, I always send star to star, but no other conditions. One half like this diagonal embedding. The tildes, you want the pullback isomorphisms. Okay. And also the factorization. Maybe it's good here to like just draw a diagram. This point is star, this point is star. Just send both map to star, and then the corresponding like pullback onto the diagonal just means like dividing a ring. And for any partition, factorization as an office. Factorization, I think, also part of the data. The M of like 2 I over U is going to be like isomorphic to like the our tensors, box tensors. You keep the module onto the last set. IN. U is the open set. Right to the corresponding to the again different coordinates in like the different subset in the partition. Okay, so this is definition of factorization. Again, quick remark is that you can also the modular model.
So that should also be a box product in the bottom line, right? Inside the parentheses, as opposed to a disjoint union.
Thanks. Yeah.
Yeah.
Okay, so this should follow. This should finish like the part for factorization algebra. Okay, so now we talk about Chiral algebra. So I'll just start like by briefly say what like my understanding like Chiral algebra is second part of Chiral algebra. Is that if you look at the factorization algebra, you know what it is over the open, like open that's like apart from the diagonal, you know what it is on the diagonal. So like to pin it down, you just need to know what's the extension. And the Chiral algebra structure precisely tells you what the extension is. Okay, so so I'll not give the definition of Chiral algebra first, but I'll tell you like how to like cook up like a Chiral algebra from a factorization algebra. That's pretty easy. And then I'll give the definition. Okay, so let's fix some notations. As I said, I have this open and closed, diagonal, or it's this J. And well, if I'm looking at like factorization algebra, then I have like B2 over X cross S. I know what's its pull back onto X, it's B1. What's it pull back onto this U is A1. Sorry, both times are A1. B. I want like an extension from like this. Okay. So let me give like a procedure of like going from factorization algebra to Chiral algebra, whatever it is. And say I start with a factorization algebra here. Okay, so first let me finish like the remark here. Yeah, so any factorization algebra is naturally like has a natural D-module structure. Okay, so well, if I consider like this, first each PI D-module structure. So as I said, it just comes from like comparing two diagonals. Sorry, two units actually, not unit like. Okay, so I have two maps. One map is like this, used like by the unit map on like XXV. And the other is a swap. Okay. The claim is that I1 and I2 are both homomorphisms over infinitesimal neighborhood of the diagonal. Well, in this case, well, X is smooth, so like the diagonal is like a regular embedding. To like show it's like isomorphism over like infinitesimal neighborhood of the diagonal, just to show it's like isomorphism on the diagonal, because you already have a map. And that is obvious by our units. Okay, and such an isomorphism from here to here over the infinitesimal neighborhood of the diagonal by an algebra XXS, it's just equivalent to like D-module structure or like just differential operators. This isomorphism, well, I mean over the infinitesimal neighborhood of the diagonal. So this is how you can. And okay, so then maybe it was so then we'll just cook up like some objects, some operations that keep track of the extensions. Okay, so let's. So there are some like change of notations here. Like I want to keep BI, but like there's some like left and right that goes on. I don't know. This the tensor like a dualizing shift. That AI equals to BI tensor dualizing shift. I want to say that here my notation is always like this dualizing shift is like the one like the actual dualizing shift like but like move to degree 0. Okay, so for example, if omega x, I usually it's like setting like degree -1. But now I just do this like at degree 0. It's like the usual like shift of dimensions. Okay, it's like different from like the upper streak by a degree. You actually see this comes up when I do like the extensions. Okay. So okay, so what happens? So then the thing is that instead of like the upper stock pullback, now like the compatibility is like more naturally expressed in terms of like the upper streak. Let me tell you why. So this is like just write down definitions. Right. And well, this part is V1. And this part is omega x shifted by 1. It's shifted up by 1. Because if this guy sits in degree -2, then star streak pullback is the upper streak pullback is like this guy sits inside degree -1, so degree 0 is 1. Okay. Well, so this is precisely A1 shift up. Okay, but we know that there is a triangle that keeps track of like the extension structure. This should be sort of like similar like to the one given B, it's just a twist away, doesn't matter. Good. Good, but now we'll get rid of like the degree shift. This will induce this triangle. Use if I start here, go here, and then go to like degree shifted by 1 here. I get like 2. Full push. New box tensor of A1. And this term should be delta streak of this guy shifted by 1, so let's say. Yeah. And in this map, or new, this map records extension. This is what I mean by like the, well, yours is called a Chiral bracket. Chiral bracket remembers like the extensions like this and this to give you like page. Okay. All right. So here's some like preliminary property of about this mu. So first, mu is anti-symmetric. This picture. And basically the reason is that like when we do like this kind of like twisted by omega x2, I want to say like the unwind definition is like basically boils down to like use like this box tensor. And like this guy is anti-symmetric. Okay. And so we also have like some sort of Jacobi property, but so the point is that this guy could be sort of as like a, well, this sequence is like a Poisson complex of the strata just U and diagonal. Yeah. But if I have like a 3 copy of X, I can also consider like Poisson complex like that has like 3 terms. Right? With the strata, like how many coordinates are the same. Yeah. So that will give you the following thing. Triple Poisson complex. Two give you the following thing. So you apply it to A3. which is like B3 tensor omega x. The first one is like, yeah, so I will abuse notation like I would, all open immersion I want to know that J. Just don't want to write that. The first one is like all three coordinates are different. Okay. The second strata is like two of the coordinates. Use J here. Yeah, should also use the somehow decide not to use them. The last term would be just the strata where all three coordinates are. Okay. And in fact, if you look at the definition, you will see that so this guy is basically the box tensor. So if we start with like a local section here, you have three ways to like get to here by going to here, going to here, and going to here. And each of them will give you like this, right? Or maybe here. Use me next one next to see this one, but like this is complex, so like the three maps sum up to 0, so this give you like Jacobian. I won't write down the detail, probably can, but this give you a Jacobian of the arrow brackets. It's this mu. Okay, so this motivates our like definition for chiral algebra. Is there a question?
So is it like, is there an example where mu is just like an ordinary Lie bracket?
Yeah, there will be a just the ordinary Lie bracket. Okay, so here are some problems. So like, I mean, if you just like take like the naive definition, like try to take like A to be like just like a Lie algebra tensor dx, and then it's not like a chiral algebra. You have to take like chiral envelope to make like chiral algebra. I'll talk about this later, but yeah, I don't think it's easy to like just take it all like. Yeah.
And in the Qian complex, I thought the maps were loosely speaking given by taking residues. Like the Qian complex I know is you have.
Yeah. This map is roughly taking residue.
Right? So I should not be thinking of it as a Lie bracket.
I mean, I don't know. I mean, in this it's like I think they have something called. I'll write something down like next. Something called like Poisson-Chevrolet complex. So if we treat it as like a Lie algebra, it's like a Chevrolet complex. But if we treat it as like a geometric setting, it's like Poisson complex. So it's like these things are kind of related. Yeah, the unit one, the omega is.
So sorry, I can't hear what people in the audience are saying, but just to tack on to Nikolai's question, it is literally a Lie bracket. Like there's a sense in which it's literally a Lie bracket, right? Like there's this kind of notion of like a pseudo tensor structure where you have in-array operations, but your tensor product is not necessarily well defined, right? So here you're doing this operation of like J lower star, J upper star of the box product, right? And so you have this notion of like chiral in-array operations with respect to this operation, and it's a chiral algebra is literally a Lie algebra. Well, a non-unital chiral algebra is literally a Lie algebra with respect to that pseudo tensor structure.
Yeah, so it's like just restricting like this to like just a box. That will give you that. But I think well, the usual Lie algebra structure, right? I would just think about it as like what box has like. This is like extending to like. Yeah, but anyway.
Thank you.
Well, I'm saying it's like there's a notion of like binary chiral operation, right? Which is like if I have D modules like M, N, and P, I can consider maps from J lower star, J upper star of M box times N into delta lower shriek of P, right? And it's just some well-defined notion of binary operation. And as soon as you can talk about binary operations and trinary operations and so on, you can talk about things like Lie algebra structures. And it is just literally a Lie algebra in that context.
Thanks, Justin. Okay, so let's skip the formal definitions of chiral algebra. Chiral algebra is just a D module, which is chiral brackets plus like a. Well, okay, so you also need like a unit. So this is something I haven't thought about, but should be clear from the factorization side, right? They use a fancy A to denote it. With what? With a chiral brackets. Where are we going from? Open parts. To the big delta A and a unit map. But now because of it, like cancel everything with like omega, and we goes to A, such that well needed to satisfy this like unit axioms, right? So the restriction of mu, so this product to so I have an omega x to A, I replace this A box A to like omega x box A, I go to delta like lower shriek of A, what should it be? It should just be the one coming from like down. Okay. So this one not necessarily come from Cousin compacted because you don't even know A is like delta upper shriek of A box A, but like A box omega like delta upper shrieks to like. Okay, so let's see. So restriction of mu to this. Is the one from the Cousin complex. The road goes to omega x box A. Goes to okay, and well, I don't have space, but like with the chiral bracket satisfying the two property we said, and the symmetry. Let's take all the identity. Yeah. Okay, yeah, so this is the formal definition of chiral algebra. I mean, let's take a break after this. So okay, so there's also like a well pretty easy to define version of like chiral module. One is similarly here, I could replace one of the A by M. Then there's no anti-symmetry, but I just so-called Jacobi identity, which basically tells you that well, it's a Lie algebra action, and there's also units. Module. Defined. For example of chiral module. Well, first is like the trivial chiral module, just the ring itself. The other thing is that you can take like the shriek stock like of a shifted by one. It's not necessarily, but like this maps today, and then you basically just restrict your mu to like over this map to like this guy, and then any box one of it maps to like this. So we won't talk too much about it, but like the actual theorem that I want to talk about today and like we will prove is that there exists equivalence of category, the monoidal category between our algebra and factorization. So basically, the thing we did here by like giving like the factorization algebra module structure, and then like use like the extension structure to give you like the bracket basically already tells you one direction, so namely going from factorization algebra to chiral algebra. Which of these are already produced chiral algebras. The next thing we do is like provide like inverse. Okay, but let me just finish it. But like if and also like there's a module version that I want to prove. A corresponds to B, then chiral A module. It's also equivalent to factorization. It's 5 now, so let's take a break. Then we'll resume. Well, we're in the midst of like proving a theorem, and we said we already constructed the functor from like factorization algebra to chiral algebra. And this direction is relatively easier. The next thing to do is construct like factorization algebra from the chiral algebra. Okay. So it's kind of well, okay. I basically I said something related to like the break, namely that well the Coulomb complex is like a trivial like that's just complex level. That's walking to 0. So, for example, if you want to produce this A cube, then you would think, well, just take like truncated version, right? So get rid of this, but then this part, right? And then if like I can prove that there's one cohomology is this, then that's actually the idea. But like now you don't just well now like these maps are like originally to have history, those maps are just correct from the complex. It's like exactly mapping like points. But like if you don't have it, you start with like the chiral algebra, then this map should be interpreted as like already solved for chiral. That's that. So so I'll only prove this. So algebra versus algebra, and one direction already be this map. So let's see. So let's define CI dot to be the thing I just said, just truncated version from like the first strata like to the bottom strata without the full code. So you want to consider a full push of like this box. Okay, I want to say what I start with. So I start with a chiral algebra. Start with my A. Take the n-fold, well, the number of 5-fold box tensor. That's my first. And then I do like this ultimate tell you what it is in 1 second, and then just write out the term. I minus 1 factorization of I. Just 2 of them are sorry, here it is. Last term is just forward of a single copy of A. Okay. but with the connection map, connecting map by alternating some. So that's why, like in this point of view, this is sort of like a Chiral. Okay. But yeah, but like if you again, it's actually the same sequence. This sequence is for like Fujian Chiral. Okay, so well, also hard fact is that on a complex level, those CI dots already satisfy factorization and also like pullback properties. Okay. Complex satisfy factorization.
Sorry, what is the indexing set in that direction?
This?
Yeah.
Yeah, this is like the do a partition of set I. Okay. Do a partition of I in terms of like number of I minus one subsets. Just like one of the sets. Complex satisfied factorization, but now it's like upper street back. Okay. It's expected because everywhere I tensor with omega. In the other direction. And well, so the claim is seem to prove. The claim is that nth cohomology. The cohomology is concentrated in degree here. So let me give it a name. Let's say this is minus n, so minus I. Well, and it's degree 2. That's where I put my complex. Degree 0, degree minus. Claim that's 0 except the augmented complex. Okay. So after you prove the claim, everything follows. Okay, then and so like omega x to the I inverse back to like get like the correct left. This will produce you a equals like Qian of dot by its side. That would do the job. Okay, so just always down to prove it. Okay, but well, for this kind of thing, it's just gotcha. On the size of I. Okay, so then we'll consider I prime. We'll reduce the dimension. Or maybe let's just say this way. Two. I call this I1. Okay. So now I can consider x I prime. Now I can wear 1 equals to 2. Okay. It's components open. I give the name, right? So I'll try to like use like the triangle of the shift to like mention because I have this upper street pullback. CI is compact CI dots here, pullback, start pullback to CI prime dots. Okay, and then forward. Triangle. The induction tells you that this guy centered at concentrated at +1. That prime is one element less. Okay, so now look at this. What is this? So this U is the place where x1 not equals to x2. Let's say you have like, so I want to claim that the pullback of Ci dot over this U is going to be can be like sort of like locally as like a factorization of two like smaller CJ dots. Okay. The claim is that okay, so let's think about x1, x2, x3. So there are two possibilities. Either x3 is not equal to x1, where I put the decomposition like this, or x3 is not equal to x2. This is my conditions. That restrict to like x1 not equal to x2. The only other case is that x1, x3 equals to x3 equals to x1. Well, then if you have an x4, you do the same thing, right? Either x4, well, let's say in this case, either x4 is not equal to x1 with the travel here. Make it like condition, or x4 is not equal to x1 and x3. The only complement case is x4 equals to x1, x4 equals to x2, or x3. One more cases, but the point is that happens. For some J1, J2 strictly less. This guy is well concentrated at degree minus J1, so at degree minus J2, well extensors concentrated at and because it's a local statement, we're just looking at sheaves, compacts of sheaves. Concentrates. Well, but sure, J1. I have like these concentrations, so there's just one thing to do. So it's minus I plus 1. You just need to show that the degree at minus I plus 1 map from the homology here to the homology itself. Now suffice to prove degree minus I plus 1 map onto it. It's like the edge to be your sheet. Not like the homology. Once I prove the map is 0, then it's must 3 minus. Okay. Let's prove this. So that just boils down to the following. So what can I do? Look at these 2 degrees, which is just like directing mapping that like the first 2 like this is my parallel bracket. Okay, so I can also restrict my attention to the following. So now I consider that like over this, which is xi, then to like 1, and consider like the same use by the unit. let me explain it. Okay, so what is V and what is I? I think V and I are here. So yeah, I is given by like x1 equals to x2, and V is given by another. So it's really like there's immediate scattering line divided by x plus x1 later. This is the chiral, multiple chirals. There's also multiple chirals. No bracket. Okay, but the point is that by the unit axiom, this guy is from the Poisson complex. There's the chiral bracket restrict to like the one given by Poisson complex, like the whole lines. Yeah. And the map from Poisson complex is where then mixing here, get back from here. It must from here to here, so it must from this modular. This is like the well, the construction of the other side, the other map, like chiral algebra. Poisson Chiral. Okay, so this will finish the part on chiral algebra and like the factorization algebra. So now we'll talk about chiral envelope, which produce a chiral algebra from like a usual E algebra, just on the most like a box has a like that over of A. That's where a lot of example comes from. Okay. So so we have like this style algebra. We module with the lead brackets. On the nose, right? So L box L with the I delta. So it's defined on the whole, but it's like smaller, right? So this guy is smaller than like. Okay. And for example, we'll just be again in the algebra G. But also, any chiral algebra, I think that should at least position like this. The algebra is the algebra structure. Okay, and the theorem is that I can hook up like a from a list algebra L, also a chiral algebra, I think the left algebra. Left algebra. This gives like a chiral algebra. Right, letting The other way. As L goes to A of L. So A is our usual notation for Chiral algebra. So A of L will be about a contour at that point. Of Chiral algebra. Oh, that for a reason is that, well, sort of like a universal envelope of L. Somewhere. Okay, so let's do the proof and see what A actually is. Give some. So I want to say that, well, this is later, but like if you apply this Chiral envelope to this guy, you would get something with fibers up like fiber over the X. So it's like a version of vacuum module over X. Or like more generally, I guess, representation of continuity.
Did you say it has a universal property? This envelope?
Yeah, the that one is just like any well, like any form from like from the algebra. Yeah. Same as Chiral. For any Chiral, that's the need. Okay. First, we will construct such a. We're going back to the like sort of induction. Okay, so that's a good sketch. I'll just tell you what the functor is. You think about I equals to empty. Sorry, I equals to just one. Then you want something like, let me just write it. It is like all coordinates here is not the coordinates here. Okay. Size. And I also have two projections. For one is equal to X, for two is equal to X. Okay, so if I is just one, I want to produce like a pole, and then I show to view and then push, which will on the fiber of here, I give you like cohomology of like a sheaf on like the punctured X. Punctured according to. Okay, so that's defined. So first, the non-punctured ones. Yeah, so let me say that I will actually produce like a factorization algebra instead of a Chiral algebra, because we just proved that they're equivalent, so that's fine. Okay. Use factorization algebra. Because I'm doing a factorization algebra everywhere, I need to like do like a reverse of like answering like a reverse of omega. But like just this fiber is like non-punctured. This fiber here is like a non-punctured cohomology of L. And the punctured ones is here. Yeah, the puncture occurs because like the Chiral bracket also happens. Okay, just pull all the way to U instead of the side. How can I do with those? Because L is Lie algebra, those are also Lie. This one is set factorization algebra at xi with a quotient universal. Every time because I want an algebra, I want to like make a universal enveloping, but you will see that somehow like the same being quotients will x by 0. So quotient. Also, like each fiber of this doesn't directly relates to like each fiber of L. And I also, but surely I want to map from L to AL. Let's see how it goes. This is more like the induction from like L to AL. But like on each fiber, you know what it is. It's like induction of the side, just pointing out this, right? Okay, so now how do I define a map from L? Okay, so the brief idea is that in degree 1, this modulo this is L. Okay? So we just add L to the degree 1. Degree 1. It's actually the whole, it is the whole degree 1. That's because I have this. Sorry, I should say I have like a L goes to BL1. Eventually, you're gonna map D to like A of L. A of L would be like BL1, like canceling omega inverse. Yeah, maybe I missed that stuff with all the. Well, so here, like the fibers. Well, if I just look at fiber, this is like echelon X, echelon X. So this will be our. Quite believable that works over the whole X. So yeah, do that out. So remind this, so I put this out. Coming from this test. Okay. And I just need to say a brief word about how you would like construct like this isomorphism. So say you have like a map from L to A, just as like the algebra. Then the algebra embedding tells you that you have like this map. Here are group star. Here I construct AL. Here are group star. Okay, then you can like do the same procedure as here. Go push, but onto the coordinates of A. So push, Y. Put forward. On this fiber, you get A. Here you get co-module of L function. And it acts on. This gives you that I have an action of the algebra action of L1 acting on. I also have, well, really messed up with A and B, but anyway. Right? Yeah. Oh no. Okay, so L goes to A, then L has omega. Wow. Anyway. Yeah, because I want to make it clear. So originally it's like the part without omega inverse acting on A, and you put it on like omega, then you have like L2 that one. Okay, anyway, so this will also give you universal envelope in algebra. Okay, well, maps can be one, sorry. I just letting L2 L1 acting on the units. I have like O goes, and the point is that, well, you also just the L2 that, so name it each fiber just a cohomology. L2 L1 0. That's by like 0. Like the units. That's something to prove, but not that bad. As a map practice, right? So, yeah, to prove that it's like factorization, like, boils down to prove because like L is like L goes with it. That's a okay, so but what's the example that we talked about? The really interesting thing is the case where applies to like the algebra given by like just like the finite dimensional algebra. In that case, I get what? I get ALX. So recall the definition is like universal with this reduction. And because I do it at X, right? So it's just somehow I take the 0 to 1 cohomology of the full back to X minus this point X. State of X is the same as the start point X here. Yes. Of the trivial. Then you have this Bruno-Lazaro like philosophy that this could be replaced as a contra disk. Contra disk. This.
Is it the stock or the fiber?
It's a stock. So we'll just be putting like the usual one to choose a pseudo-divisor. So uniformizer. Virtual strategy. This is exactly the back end one. So okay. Yeah, after some, yeah, I did this. That's not precisely G hat. Maybe Kevin would tell us that it's a direct determinants here. No. Okay. Oh yeah, exactly. I don't. Yeah, I can just start with. Yeah. Okay.
Wait, why can't you start with like L's G hat?
But so almost done. So one, and like this section about like arrival, I would just want to like briefly mention a theorem of like telling you how to compute like the factorization homology we introduced of like the parallel. I don't know how to convince, but I think somewhat can ask me. Well, basically, this is like topology. Look at like the parallel homology of the parallel of this algebra. That's the same as thing what I mean. So this is like the homological Chevrolet complex. Now in the D module and also these algebras, we take like the round complex. This will be like the D algebra. Like at the back. Okay. And for these algebra in the back, I have this Chevrolet homological Chevrolet complex. That's this resolution that computes like the derived for optic coordinates. Okay, so the last part I want to talk about like this sort of like this argument you use to prove like homotopy groups are like of like degree larger than 2 is like Eckmann something, sorry, I don't remember the name, but what we're gonna do is like commutative algebra.
Eckmann-Hilton.
Hilton, yes.
No relation to Paris.
Okay, so commutative parallel. Definition is that is commutative. If like the parallel bracket, when you restrict it to like just a box A, viewed as a least algebra, it's like vanishes. And the mark is that it's equivalent to just, well, what's the co-kernel of this guy? It's like the thing given by the cosine complex. It's like equivalent to like factorization. Sorry, equivalent to like new factors in like it's the delta proportion. Now, would also denote like the inner part as like the shrink tensor product. Proposition is that commutative algebra is equivalent to commutative. that one give it was pretty easy to just send A to like without this back. And then this brackets, when you do like Schrick tensor product between, it becomes star tensor product, and anti-symmetry of the like chiral bracket becomes like actually symmetry. Anti-symmetry becomes symmetric again because of like this identification like omega x to omega x box. Comes from that. Okay, so well, commutative chiral algebra is pretty easy to control. Just have 3 modules. And actually, we have a good criteria to like tell like out of some cases how we prove it. Namely, I'll state this theorem first, and then I can go to A be a chiral algebra. If you have like a unitary binary operation, another product, something about it as a vertical product, as a compactable with the original chiral bracket, then everything is commutative. Vertical product and the horizontal chiral bracket are both. So that A be a chiral algebra. Compatible unitary binary. Compatible unitary binary operation. From this big tensor product to A. Then the claim of this theorem is that A itself is commutative. And I will just write like the mu for A equal to M, in the sense that, well, if A is commutative, then it's factors to this guy. And then I can talk about mu. Yeah, and I forgot to say that the two product is this. That's what the proof of that idea that by usual algebra theory, such an operation is a vertical. And what does compatibility mean? Compatibility just means you have a CD. This is vertical product, this is vertical product, it's horizontal. Horizontal compatibility just means I can do this product first, and then the product of the product vertically. This is both contract, and also the horizontal. That's what compatible means. Okay. And the point is that then you know that, well, then okay, so the two algebra multiplication both has units, and the units coincides. By just looking at this. This one is for like vertical, horizontal. And if you run these two equality, you get one. The units coincide, I just denote them both by 1, and I consider 1 equals to S 12. Yay. And like the proof is just a complete copy of that. I'm not sure what I should put. Yes.
It's fine if you go a few minutes over. It's fine if you go a few minutes over.
Yeah, I don't have. I mean, I'll just write. not that enlightening anyway. Yeah, the proof is just well, it's problem. Then you're just looking at, well, I want to copy like this diagram. I think once I write on this diagram, M is the extra vertical. Use my original table. That's what the compatibility is saying. Then you just prove the omega alpha is 2 units. Winding. This on the like the left diagonal, you run this, you'll get omega like, and then like this, and then like this. But yeah, so this is the Eckmann-Hilton arguments, which tells you the theorem. Let me briefly say something about like where it is used. I'm not going to prove it. Where it is used, that might be useful later. Mark. This can be used like to give another like description of like commutative Chiral algebra. So for commutative algebra, so used. So the commutative Chiral algebra is really given by a factorization. Commutative Chiral algebra is given by factorization algebra. The factorization algebra corresponds to this Chiral algebra is actually given by the global section of multiple jet space, multi-jet space. The I corresponds to the number of jet states. It's basically proved by like saying like this algebra structured on like this global section is compatible with the Chiral structure, and then you must have that. And one more remark that I also say is that in the commutative case, algebra, there's yet another way of like computing like the Chiral homology. Namely, I think you would have like a stack of these from then the Chiral homology. On the derived sense global section of the section space of the map. Okay. But only in the commutative case. These are the two things that could be useful, but I have no idea. Or at least this part I have no idea. But yeah, I think I'll end.
you say a few more words about the first three more?
Yeah, so
So you mean like jet spaces of the curve?
I mean that's what I do in space. Associates to any. That's I want to scheme over XI, so that's basically now okay, I think that's that we did it on at the high side. The ARB, I don't.
So this is
That should be also like any comment. Yeah, there's this proposition I raised, yeah, so any
so this is like the sorry, I hope I'm not cutting anyone off. I can't really hear the audience. This is the full space of jets. A commutative factorization algebra is functions on sort of horizontal jets, right? Like the jets, if you just is the I see that's what I see because like jets is some big infinite dimensional thing, but right inside you're considering the ones which are sort of horizontal along the curve, and that'll actually have finite dimensional fibers. So these are sometimes called horizontal jets. Yeah.
And that's like the only example of a commutative D module.
Commutative chiral algebra. Yeah, they're all this one. One other remark about applications of that Eckmann-Hilton principle, it was actually already used in the seminar in a sense in Chiral's talk. So at least that's one way to prove commutativity of the endomorphisms of the vacuum for Kac-Moody, right? Yes. So it's a nice way to prove that.
Yes.
But it's not for geometric attack. It's convolution product.
That's for a category, right?
Right. Okay.
Saying I could those
there's definitely kind of I mean, I don't know if it's not like literal, but there's sort of a heuristic connection to this story that you can tell about Satake. I mean, what's going on with this Eckmann-Hilton argument, right? Like factorization algebra is analogous in topology to an E2 algebra. And I mean, it's even kind of they're literally connected via Riemann-Hilbert. And what happens when you have this kind of associative binary product, right, is that you're introducing an additional multiplication, so it's sort of an E3 algebra, right? And so if you have such a thing and it's classical, like it's concentrated in cohomological degree 0, then it has to really be commutative, right? The associative product has to be commutative because it's, I mean, then it's kind of literally the usual Eckmann-Hilton argument, right? Like, but yeah, and so it's kind of similar to the story I, have mentioned before about Satake, which is like the reason that the kind of heart of the spherical Hecke category is symmetric as a monodal category is because the spherical Hecke category is on the one hand factorizable, so it sort of has an E2 monodal structure. On the other hand, it has convolution, which is an E1 monodal structure, and they're compatible, so it's really E3. But then if you have an abelian category, which is E3 monoidal, it's actually symmetric. So E3 equals E infinity for kind of an ordinary category.
Justin, just a question. Like you said, like with using the fact that degree 0 is that's supposed to work also for any class of factorization algebra, like we take Riemann-Hilbert factorization, right? E2 for algebra. What? Sorry? The list of the factorization the list of factorization yeah. Yeah, you cannot create.
Any other questions? Maybe from Zoom? Comments?
Thanks, Lee. Gotta go.
Thank you.
Nice talk. Bye-bye.
Thank you so much, Lee.